Kia ora koutou te whānau. My name's Matt Highway.
Kia ora, I'm Kevin Cote.
We want to talk to you guys today about this really cool thing that we've developed called, well, we think it's pretty cool, called the LandScanner, which is an artificial intelligence and satellite-derived tool. And today we're going to go through a couple of things. We've got Kevin here, who's a data scientist and expert in this remote sensing kind of realm, so we're going to do an introduction to remote sensing. Then we're going to talk about our little LandScanner project around how it sort of is solving some of the information gaps that we have in nature-based solutions, catchment management. There's some time for Q&A, so hopefully you've got plenty of Q&A after that, and please be critical of our project. And then we're going to ask you to get into sort of helping us solve the next step for our development project. So that QR code there, if it has only a few questions in it, if you want to have a look now, that would be great. It just goes to a Microsoft form. We'll come back up later on as well. You can go into the draw to win a $100 Prezi card, something like that, and a few other prizes as well. So really encourage you to give us some feedback. Thanks.
All right, so I wanted to do a very quick background of what remote sensing is, because I know a lot of people are familiar with it, but just to sort of have everyone up on the same page. So in general, what is remote sensing? And a lot of us think of it as satellites and drones flying around us, taking pictures of the world as we are just doing our everyday business. And in a lot of sense, that is correct. It's being able to capture data and continuously capture data as we're doing our everyday lives. And usually this is through satellites. That's a really common method of remote sensing data. But more often it's aircraft, as we're used to with the national coverage of the LiDAR data, or drones that a lot of people have used for sort of more fine-scale mapping. There's a few benefits and a few downsides of remote sensing, so I just wanted to touch on some of these so that everyone sort of knows a bit of the limitations around it. Excuse me. One of the great benefits is the area accessibility. Having a satellite, you're not limited to having to go by foot into these sort of back areas that you can't really reach to easily. The satellites are capturing data of every single part of the entire world, really. So it's a great advantage that you can get data into some of these areas that you can't easily sample on foot. Also, the repeat measurements. There are some providers, Planet Labs is one of them, who has many satellites in the air and can get a repeat measurement of the entire world in about 3 days. So every 3 days you're capturing new data, which you can imagine can be very beneficial when you want to look at change over time and sort of how these different landscapes are changing or capture events that have happened. And finally, the consistency is a huge thing. You're not relying on the exact same measurement to be captured using the same method by hand. Satellites aren't changing, they're capturing the same exact data. This is mainly true for airplanes and drones as well, subject obviously to the operators and whatnot, but you have a lot of consistency to be able to start looking exactly how that landscape is changing through the data. There are a few downsides, and in New Zealand we suffer a big one of cloud cover. Often you can't see what you can't see. Even though it's a satellite, you can't see through clouds in a lot of cases. There's an asterisk because there are certain satellites that can penetrate through clouds, but for the most part it's based on visual aspects. So even though the satellite comes over every 3 days, if it's a cloudy month, you might just not have any data for that month. So it's a bit of a downside you have to play up with. Cost is, it's a bit of both hands. There are openly available and free satellite data, but if you want to get into the really fine resolution, think of something that you're used to seeing on Google Earth per se, you end up paying quite a bit to have a coverage of a large area. It's usually charged out in per square kilometer or per hectare. So it's something to keep into consideration, which falls into the next point of detail. Satellites at their finest can get down to about 40 centimeters per pixel in the image. So if you think of it, you can probably see a car, definitely see a house, sort of objects in that sort of size from satellite. When you're looking at the open and free ones, they're up to 10 meters per pixel. So that's now, okay, you're looking at a smaller paddock and bigger, sort of in those sort of ranges. There's a trade-off with drone imagery. You can get much finer detail because you can get closer to the Earth, but you can't cover as large of an area. So there's always a bit of balance there. And then what can we do very quickly with remote sensing? The biggest thing is combining different types of data together. You can get data about land cover, land use, filtered, combining with soil moisture data, combining with elevation data. And you can start to really put all of these different sources together to get a more clear image of what you're trying to pull out and discover as part of the analysis. The change over time is a big one. Again, consistent data over and over and over. So you want to see how your landscape's changing throughout the year. It's a really strong tool and a really strong way to be able to do that. And then, again, AI has been mentioned a number of times today already, but it is a big factor. It's a way to combine large data sources and complex data into a very visual and easy to understand sort of way. If you do want further information just on remote sensing specifically, there's a couple books by John Jensen that are really good to read. Also, a shout out to the PC. There's a report that they're going to put out in sort of April, May regarding remote sensing around Aotearoa, limitations, uses, et cetera. So keep an eye open for that. Hopefully I'm allowed to announce that. I'm not sure they're here anyway, so we won't tell them.
They are here today.
Well, here.
Oh, hopefully in the next door. So Kevin's very humble as well. He's one of the co-authors on that paper as well. So yeah, take a look at that next year. So I guess we've got this tool that looks at satellite data, uses remote sensing, artificial intelligence looks at the data, but I guess, yeah, what's the point of it? Why did we even kind of consider this? And I guess the challenges that we thought we were addressing were, if you go to the next slide. There's I think Cyclone Hale and Cyclone Gabriel probably highlighted stuff we already knew in this audience, was that we do have lots of extreme weather events. We do have to respond really quickly, but often we are doing that in really data poor ways. We don't know exactly where in our region or our country or our catchment things are happening, so we're just doing the best with the information that we have, given those sort of emergency situations. We also, across the country, this has come up quite a bit today, apples with apples. What satellite data enables us to do is have consistent information and consistent approaches across the country or even across the globe. So it's a really useful way to compare, understand our environment consistently and apply consistent solutions.
And then I touched on this one already, but the ability to actually detect that change, it's a massive one with our ever-changing climate, landscapes, land use, et cetera. We're moving. We need to be able to detect that change, and that's kind of what we aimed to pick up to give that data back to the people making decisions on the ground. And then finally, adding more information to these larger decisions being made. Quite often, you have great landscape, large landscape changes, decisions being made on point data from different parts of that landscape. This gives you the opportunity to really have that holistic view of the entire catchment as you're making those sort of decisions.
Cool. So yeah, like what do we do about it? What is it? What did we think we could do to address these challenges? And we've got 3 core kind of services that we've developed through this product. Really, the first one is around weather, kind of not detection necessarily, but sort of understanding after an event what the extent of that impact was and what the impact was as well. So because we've got this kind of consistent data going across the country, we can, through AI, look at the landscape post an event. So where was the flooding, where was the erosion, where was the wind throw, that's come up a couple of times today. So you can look at things in the landscape pretty quickly and sort of prioritise what you're doing. There's also, understanding landscape change through time. So I know in many cases we're pretty good at this, but you can imagine a flyover a region is only every few years. We can plot sort of change at a much more consistent rate. And if you think about things like in that photo there, intensive winter grazing, it happens seasonally, it happens in different parts of the landscape. You can track things like that pretty quickly as they occur, or cropping or whatever it might be. And finally, I guess what I think is really good for this audience is being able to track progress for our own projects. So lots of projects we do across the country, within catchments, within regions, and to be able to sort of show the on-the-ground action or benefits of whatever it might be, an education program or a marketing program, and seeing that sort of on-the-ground change occur in relatively near time is really useful. So those are our core services.
So what we wanted to do was tackle the number one that Matt brought up was flooding. It's a big area that we have fairly good knowledge in already. However, a lot of those maps that we're using are based on sort of modeling approaches, predictive modeling, what should happen based on the landscape kind of thing. And what we wanted to do was add a layer of detail of what did actually happen after these rain events. So for this case, we looked at sort of 3 major events, one of them being Cyclone Gabriel, and grabbing data as soon as we could to measure where the standing water was after these major rain events. And we can do that through a satellite technology that uses a radar reflection to pick up on standing water. So we're looking outside of sort of the known waterways. Where is there standing water on the land after these major events? What you can see there is a region sort of up in Auckland, where around this riverway there was a lot of water inundation. The water couldn't leave after this major raining event, and so we were able to capture that and map that, and then continue that process across the entire region as well. You can then overlay that with different land use types to see what sort of land use has been affected by these major rain events.
Yeah, just to add one quick point to that, from an operational perspective, we can, unlike some of the numerical models that we have at the moment, LiDAR or whatever it might be, we can track things that actually occurred in the environment over the last 8 years. So we can predict now somewhat, if it's happened in the past, this is where it might occur in the future. And you can see we've overlaid these several years, 2021, 2, 23, and 25, and just shows where the cluster of that flooding might occur. So we can start to see in the landscape which our hotspots might be for ponding water, and maybe do something about it, make good decisions. Of course, you can track that against things like, what was the direction of that rain event? How did the environment respond to? So, yeah, we think it's pretty useful in that regard. Thanks.
I think one of the neat findings, too, from this was a lot of the modeling approaches for flooding areas were based on river inundation and whatnot. We actually picked up a lot of standing water in paddocks, especially tilled paddocks. This is around sort of the Pukekohe region, where there's a lot of just bare soil, essentially, due to farming practices that couldn't dissipate the water well. So it's a flooding classification in a very different sort of aspect, if you will. The next thing we wanted to do was map vegetation and sort of how vegetation has changed. So that's sort of 2 classifications, which are your exotic forests, plantation forests, and then native forests as 2 separate categories, because we wanted to see how that land use is changing and then link it sort of with soil and erosion risks throughout that. What you can see here is a exotic forest plantation that was partly felled from 2019 to 2024. In the bottom right, essentially all the pink showing through was forest that has changed land class. So that's all been fallen and cut down, used for other purposes. But we're able to track those on a quarterly basis throughout the years from about 2017 to current.
The cool thing about this, so we really just look at 3 types of vegetation, one being pasture, one being native forest, and one being exotic pine forests, essentially. But the cool thing about it is you can track change through time, and this is just like a triaging or a heat map that we've used in the Auckland region. So you can see the red there is sort of a negative change, and it's not a huge amount. It's up to kind of 1% change per square kilometre. And the green there is a positive change, increase in that attribute per square kilometre. So you can see over time, so between 2017 and now, where that change in the region is occurring. So it's quite cool. Like, it enables you to sort of think about, hey, maybe there's something going on. For example, in the southeast corner there's an increase in native forest, a decrease in pasture. I wonder what's going on. We can track that, or we can report it, or we can use it as business cases or whatever it might be. But certainly it's a great triaging tool in that case. Thanks. So the last example is bare soil, and Kevin will go into this a little bit more. So bare soil is a massive one for our core services within NZARM, looking at erosion. But of course, we can track things like cropping throughout the landscape. So it's a really, really useful one, a good indicator. You can see here, this is around Pukekohe, where there's a huge amount of cropping, of course, for producing lovely potatoes and things like that. So we can track that changes through time, where that's occurring, and we've covered that. But the other thing that was really interesting, and I don't think this has been done before, is looking at bare soil in response to drought. So you can see the graph there on the right-hand side. In 2020, Each of these lines is a large catchment within Auckland that's been chopped up. It's called, just a catchment receiving environment. And the highest point here is the Kaipara. So with up to kind of 35% of their entire catchment being in bare soil during that peak part of January 2020. So that's just showing how much variation, I suppose, in kind of these drought-like conditions are within a region, but also the extent as well. So certainly useful for gathering that kind of information from farmers as well, just in a general sense. Thanks.
And it was actually quite neat to see, because we're doing it on a quarterly basis, you can sort of see that seasonal variation throughout the year as well, as it's changing. So that was our mapping of bare soil across everything. What we wanted to do is split that up a little bit, because we have paddocks bare soil and then we have potential land erosion bare soil. So we wanted to introduce slope into this data. So what you're looking at there is a slope map. The brighter the color, the steeper the area is. That was our first layer. We can then overlay what we've detected as bare soil on top of that and start to build a bit more of a picture, if you will. What we can then do is pull in things like streams and waterways from these known sources, different GIS layers, to start, again, adding that picture, which then allows us to pull out your highest priority areas. So these are your bare soil areas that are on a steep slope that are near a waterway. If you're going to sort of prioritize one thing to look at, those are your kind of key areas that you should be aiming towards.
Sorry about that, just checking the time that we had, and we don't have much time for Q&A, so we'll go through this really quickly. So in summary, we hopefully can measure unmeasured things and make really good evidence-based decision-making.
Giving an eye on the entire region, adding data from not just a point source, but really being able to look at the whole region, and then measure success, trying to grab that data that's out there and turn it into something actionable by the people on the ground. That's all from us.
I'm sorry, there's only time for one question. I really apologise for that.